moving on to chapter 8. With chapter 8, I'm going to put in these two sections together. I'm not going to spend too much time on polar coordinates just because once we get to equations, we're going to be doing a lot of polar coordinates. So I wanted to just double them up. And then hence polar. We got the Coca-Cola bear here with us. Now, polar coordinates, it's going to be completely different than what we've done up to this point. So everything we've done up to this point has been the rectangular coordinate system. And how does the rectangular coordinate system work? Well, that one we luckily know very, very well. Right? Everything is done up, down, left, right. In other words, like a box. Right? So we had an x coordinate, and then you'd have your y coordinate, and that's how you would get to a particular point. By either going up, down, left, right, and then we would use our x and y table to help us find points for a particular equation. Right? The coordinate itself was an ordered pair. We would start at the origin, and then you go positive or negative for your x, and then positive or negative for your y. But for polar equations, things are going to be done circularly, if I'm saying that correctly. Think about like a submarine, right? That submarine has, when it's sensing if there's anything around it, I forgot what that's called. It's a sonar, right? But the sonar isn't looking at things up, down, left, right. It's looking at things circularly. And that's exactly what's going to happen when we get to polar equations. Now, instead of x and y, polar equations are going to use r and theta. You can almost think about it as saying like radius and then the angle, right? But we're not drawing, sometimes we're going to be drawing circles, but not everything is going to be a circle. So it's not necessarily a radius. But the idea is going to be that just like how we did with the unit circle, we start at 0 and then you begin your angle. So that would be your theta. And that's the one thing that I do differently is I actually plot theta first and then I apply my r. And then r is just how far you're gonna go in in that theta direction, and that's how you get to a particular point. Right, that same point. Let me actually just, let's say if I switch this up. Right, let's say if I'm trying to get to point here, this particular point, right? Now, if this was a rectangular coordinate system, let's say if this was 1, you would go as far as 1 for your x, and then you would go as far as 1 for your y, and that's how you would get to that exact point. Now, for a polar coordinate, you would actually go as far as 45 degrees because it's perfectly diagonal, and then you would go in the r direction. So switch it, zoom in a little bit. Go here, resize this. And we don't know the exact distance r needs to be to go to this point, but there would be ways to find it, or it would either be given, but that's going to be the idea. This is our how our polar coordinate is going to work. Let me lower this. This is our polar coordinates. And we'll do a couple examples of these polar coordinates. Again, instead of x and y, we have r and theta. And one thing to add is I usually, to make things a little bit easier for me, because the nice thing about the rectangular coordinate system is that you can count 1, 2, 3, 4 in the x and y axis easily. But if we're going to be going diagonally sometimes, it's difficult to count 1, 2, 3 diagonally. So making a circle that has exactly length 1, it makes it easy for those angles or those radians that are like within those quadrants. So I usually just, luckily my iPad lets me make nice circles, but I usually make these circles to help me with these points. But this is still just an x and y axis. We're just approaching it differently. We're just choosing to go start at 0 and then rotate around this. But a couple things about the rotating. So let's make a quick note. Right? We have to be mindful of theta. Right? This, we already know this information. And I'm going to use Mr. Googly Eyes in a little bit to help us. So, real quick reminder, let's not forget that when we rotate in the clockwise direction, we know that theta is less than 0, meaning theta is negative. When we go in the counterclockwise direction, that is when theta is positive, right? So in other words, negative, right? The same way we did before, that same concept still applies here, how positive and negative works for clockwise and counterclockwise. Now the new one, the new information is going to be dealing with R. So this is actually more something we had to recall. So let me actually switch it. This is information we already knew. The actual note, I would say, is going to be dealing with what the difference between R being positive and negative. I'm running out of room here. I'll just bring this down even further. I just like having this on the side so I can copy and reuse it. So, what happens when R is positive or negative? The best way I can describe it in words would be R is positive when you move forward. I'm going to describe what I mean by that in a little bit. And when R is negative, I would say you move backward. And the reason why I say backward and forward is because I want you to imagine yourself in this graph, inside that graph, like being that sonar in a way. And you are the one doing the rotating. So this is positive, and this is negative. Right? And that's when I will use Mr. Googly Eyes. Because everything we do is going to start at 0. and we start and facing the direction of 0, right? So I want you to imagine yourself being in the center of this graph, right? Being at the origin, and you're facing in the direction of 0, right? So we're going to assume this is the forward direction, the direction you're always facing. If you were to actively put yourself at the origin and face towards 0, that's always going to be your positive direction. Backwards, I literally just mean behind, right? If you're facing one direction, we know what behind would be. And sometimes this gets confusing because in one situation, the direction you move can be positive, but if I rotate this 180 degrees to face the opposite direction, now if I were to go in this direction, that would be the negative direction because now I have rotated. So imagine yourself facing 0 and then you spin 180 degrees. What's behind you now would be the negative direction. What's in front of you is always the positive direction. And that's always going to be the case. Doesn't matter how many times we rotate. Now, obviously the rotating, if you rotate in the clockwise direction is negative, counterclockwise is positive. But for R, the direction you're facing, so imagine the direction these eyes are looking is always looking in the positive direction. That's where you're looking, always in the positive direction. But whatever is behind you is the negative direction. So again, just think about that. Think about you just being at the origin and you're rotating. In front of you is positive, behind you is negative, right? And you don't move from the origin until you know what direction you're going, right? And that can be a little confusing because sometimes facing in quadrant 2, right, can be the positive direction. But when you're facing quadrant 4, quadrant 2 is the negative direction. And so on and so forth, right? That's where it can get a little confusing. Because I could be facing where the negative y values are on the y-axis, but that would be my positive direction for my r. So again, just think about you always face in the positive direction. Behind you is the negative direction. So we're going to move googly eyes out of the way, and we're going to do some of these examples. And hopefully that made some sense. So this would be pretty quick. I really want to get into just looking at equations, but I want you to have an idea of what it is to plot coordinates, polar coordinates. Just the same way you first learned about the rectangular coordinate system, you plotted a few points. Now if you want to pause the video and attempt to do any of these before you watch it, you're more than welcome to, just to see if you are getting the idea correct. Right, or watch me do one, pause the video, and then try to do the rest. So if you notice, here's that r and theta. And some of these r's are negative, some of these thetas are negative. So it kind of is grouping all the different possibilities. So let me rearrange things a little bit so I'm not taking up too much room. I'm a little organized. Okay, let's bring Mr. Googly Eyes back. So I can have everything in one frame. Now, we'll start with A. So, like I said, I like doing my theta first, my radian. So resize. So again, we start by facing in the 0 direction, and then we have to rotate pi over 4, which we know that's perfectly in that diagonal direction, right? Splitting that quadrant perfectly in half. But my R is -2. So even though I'm facing in quadrant 1, the direction I'm facing, the direction this is looking right now, this is the positive direction. Backward is the negative direction. So I know, even though I'm looking at pi over 4, so that would be something like this, right? I rotated to pi over 4, but I went back. Let me just center this. I go back to -2. So from the origin, I'm going to go 1 and then 2. And this is exactly that point. This is point A here. As I rotated, pi over 4. But then I went back -2. Hopefully that made sense. Or you could just think about I went back pi over 2. So if you want to pause and try any of these other ones, you're more than welcome to, but I will continue the video. So for B, my theta is actually negative, so that means I'm going to go in the clockwise direction, and it's 5 pi over 3. Remember, the 3's, I can just halfway count 1, 2, 3, and then I can do 1, 2, 3, 4, 5, 6, and then go back 1 to 5. Or I can say 1, 2, 3, 4, and then 5. However you want to do it. But going 3, 6, and back 1 is quicker for me. So that is going to be, and then it's +2. So that means I rotated, right? I went here and I rotated in that negative direction. And then I'm going to go as far as 1 and then 2. And again, I'm doing this by hand, so nothing's perfect. But hopefully you're understanding how I'm getting to these positions. I'm going to do it with tally marks. So I'm going out as far as 2. And there's my point. I'm sorry if you're hearing background noise. There's a lawnmower outside. So here, if I change the color, let's try doing purple this time. Once again, same thing. So 4 pi over 3, this is positive, so I'm going to rotate in the positive direction. Let's not forget, we face, right? Let's bring googly eyes back. Right, I'm facing at 0, and I'm rotating 4 pi over 3. So once again, that's 1, 2, 3, 4, and 1, 2, 3 to go halfway around, and then a little bit more is 4. But then it's -3. So even though 4 pi over 3 is facing in quadrant 3, -3 tells me to go back. So I'm going to be going back to quadrant 1, and that's to 3. Now that's the same direction as our blue one, but blue went as far as 2, purple's going as far as 3. Again, we rotated, but then we go back 1, 2, 3. And last but not least, you want to be careful sometimes, because looking at this example, you might think that this is just a regular coordinate, but this actually says this is a polar coordinate. So make sure you pay attention to that, because we are looking in we start at 0, but the theta is 0, meaning I'm not going to spin at all. There's no spinning. I'm going to stay facing in that 0 direction. But then IR is -3, so I have to go backwards to 3. So something to keep in mind when you're doing this, right? Your face always facing in the positive direction, but negative is always going to be behind you, right? Doesn't matter how many times you spin. You can spin an infinite amount of times. Forward is always forward, and that's a positive direction, and negative is always backwards. Now, we're going to take this information to help us graph our equation. So again, that's how polar coordinates work, and that's what you do a little bit in 8.1. I'll give you some examples to try, but I really want to get into talking about an equation, a polar equation. So we're going to graph. I'll do one example, and in the next video, instead of just trying to always graph, we're still going to graph, but instead of having to use so many different points, right? Because when you first learned how to graph any equation in algebra, you started with a table to help you graph it. But this can be tedious. You can see how it can get a little confusing just doing a polar coordinate, let alone trying to graph an entire equation. But that was true for when you graphed parabolas, right? For like x squared, or graphing cube root of x, graphing x cubed, right? Once we had an idea of, just by looking at the equation or symbols or powers, that was enough to tell us what the shape should be. So at a couple points, we're able to graph or sketch the graph similar using transformations. So I'm going to take a similar approach here, is to try to recognize some patterns, or recognize or find what detail in the equation is telling me what that graph should look like. The same way for x squared, you're looking for a square. X cubed, you're looking for that cube root notation, right? And that's the same idea I am trying to do here, is looking for that information that's going to help me graph. So I'm just choosing a bunch of points, and that's the tedious part about this, is you have to, if we don't know what these graphs are going to be, we have to sketch a bunch of points. So starting with, we'll start up here. So like I said, I always like starting with theta and then finding our r. So it's a little backwards, right? Because we always are on the left and then we found the right, but here we're finding the right and then the left. You could do either or, but this just makes it much nicer for me. So for example, 3 times cosine of pi over 3. Well, luckily, I know cosine of pi over 3, and this is why we spent so much time at the beginning with our unit circle, because hopefully at this point you can get to cosine of pi over 3 is 1/2, and that's going to leave me with 3 over 2, and then 3 times cosine of pi over 4 is 3 times square root of 2 over 2, which will be 3 square root of 2 over 2. Cosine of pi over 2, we already know, is going to be 0. 3 times 0 is 0. So again, this is why we have to know our angles, our thetas, really quickly, so we don't spend so much time doing these small calculations. Now, I did say the goal is that we are going to be looking for the key indicators on the equation to tell us what the graph should be. But sometimes, to reassure yourself that you're doing this correctly or the graph that you sketched isn't wrong, you can always use the table to try to match up what you graphed and what point you found using this table. And then 11 pi over 6, right? Sometimes these can still be a little challenging. But remember, if we're at 0, I go 6, 12, and then I go back 1, right? And then I know it's 1, 2, 3. That's the same as this point. So I know we're looking at the x is 3, and it's positive. So I know there's going to be 3 times square root of 3 over 2. Now you're wondering, do we need this many points? Well, let's see. We're going to try to sketch this equation here now. Right, I'll bring googly eyes just in case I feel we need them. But we go to pi over 3. So pi over 3 means rotate to about here. Right? We're going to rotate to pi over 3. Let's just say that's roughly here. And then we're going as far as 1.5. So again, without these circles, 1.5 would be difficult to plot, right? This is about pi over 3, and then 1, and then between 1 and 2 is a half. And now I go pi over 4, which is at this perfect diagonal, right? So I'll initiate the perfect diagonal. And then this goes as far as 3 times square root of 2 divided by 2. So for something like this, we're definitely going to need a calculator. So let's bring a calculator in. So we're trying to find what 3 times the cube root, the square root of 2. So we have this as our answer. So we have 4.2. And then we're going to divide. I don't know if it lets me choose the previous number, or there's no way to write the answer. Okay, just kidding. I'm going to put this in parentheses instead, so then I can put divided by 2, and we get 2.12. So this is approximately 2.12. If I go back, 2.12 is just a little bit past 2. Just a little bit. So it's right here, I would say. Just barely past it. And then we have at pi over 2, this way it's 0. So it means we have a point here at the origin. Let me erase this. And then at pi, we have -3. So that means I rotate towards pi. That's the positive direction, -3, but I would have to go backwards to here. Now, for some of you maybe here, you might know what this answer should be. But sometimes that's not enough to help us see what that's going to give us. Right? So sometimes you need to use different points. For example, that's where we had pi over 6. But then we don't know what 3 3 times the cube root of 3 divided by 2. But I have my calculator here. I'm just going to replace that with a 3. And that is 2.6. We're going to round that to 2.6. So this rounds to 2.6. And this is the same value, so 2.6. So that means when I go face in this direction, right, pi over 6 is here, I go as far as 2.6, which would be more than 2, but a little less than halfway of that. So I'm going to say here. But at 11 pi over 6, which is, this is pi over 6, this is 11 pi over 6, I'm going that same exact distance. So that's going to be somewhere right here. And maybe this isn't enough, but for the sake of time, this actually makes a circle. And of course, my graph isn't perfect. I should have made this point more here. But this makes a circle. And I can show you that. Oops. Also using Desmos. I can put R equals 3 cosine theta. And if you notice, that circle goes up to 3 on the right side, and that's exactly what we graphed. If we're looking, the exact graph we have is 3. You can see the 3 on this part here is 3, and the same on that graph. But again, this video has gotten a little long now, just because there is a lot to put. Now, if you want to try graphing one that's very similar to this, of course, I'll give you practice to do so, but if you want to try one, try doing what 3 sine theta would do if you want to try it using this table. And I will make another video later now illustrating what are the key points to recognize, knowing that every time you see something on this form, it's going to be a circle. So stay tuned for that. We'll get back.